Next, we're going to look at angles between planes and the distance between planes. So two distinct planes in a 3-space are either parallel or they intersect in a line, and the angle between two intersecting planes from 0 to pi over 2 can be determined from the angle between their normal vectors. So if n sub 1 and n sub 2 are normal to two intersecting planes, respectively, then the angle theta between the two vectors is equal to the angle between the two planes, and it satisfies the following equation. Cosine of theta, the absolute value of n1 dot n2, divided by the magnitude of n1 times the magnitude of n2. Now, if you have two planes with normal vectors n1 and n2, they are perpendicular when n1 dot n2 equals 0, because that means the cosine of theta would be 0, and theta would have to be a 90-degree angle, or pi over 2. They're parallel when n1 happens to be a scalar multiple of n2. And if you were to work on that one, you would get that theta was either 0 or 180, depending on what sign you have on that. So let's do an example. We want to find the angle between two planes, and we want to find the parametric equation of their lines of intersection. So for the first one, the constant doesn't really matter when we're looking at the vectors. So n1 here is going to be 3 to negative 1, and n2 is going to be 1, negative 4, 2. So the different pieces, we know we need the absolute value of n1 dot n2. We know we need the magnitude of n1, and we need the magnitude of n2. So I'm going to find all of those pieces. n1 dot n2 is going to be 3 times 1 plus 2 times negative 4 plus negative 1 times 2, which gives me negative 7. The magnitude of n1 is going to be the square root of 3 squared plus 2 squared plus negative 1 squared, which gives me the square root of 14. And the magnitude of n2 is going to be the square root of 1 squared plus negative 4 squared plus 2 squared, which is going to be the square root of 21. So this right here then becomes the absolute value of negative 7 divided by the square root of 14 times the square root of 21. And we can do some work on this. Absolute value of negative 7 is 7. Here, if I combine this into one radical, we would have 2 times 7 times 7 times 3. And of course, those two 7s come out front to be a single 7, and we're left with the square root of 6. So this cancels, and we get 1 over root 6, and then if we rationalize that, we get root 6 over 6. So now we actually want to know the angle here. So theta is going to be the inverse cosine of root 6 over 6, and that's the absolute value of that, but if you want a decimal approximation, that is 1.15 radians. Or if you needed the degrees, you could put that in degree mode. So that is the angle between the two planes. Now we also need to find parametric equations of their line of intersection. So remember, this comes back to needing a vector that is orthogonal to both n1 and n2. So my direction vector, and that's the reason for that is because these are normal or orthogonal vectors themselves, the n1 and the n2. So if we want to find the direction vector, we want one that's orthogonal to both of them. So n1 cross n2, we're going to do the cross product. And I've just copied the two vectors from the beginning of the problem, and I copied my first two columns because I'm going to use the diagonal method. So now I've done the diagonals, I've distributed everything, so I get negative 7j minus 14k, which means a here is 0 since there's no I term, b is negative 7, and c is negative 14. So now we need a point, and it doesn't matter, we just need a point of intersection. So I'm going to find a P that is on both lines, or on both planes. So we will find a point of intersection, and I'm going to start with 3x plus 2y minus z equals 7, and x minus 4y plus 2z equals 0. We don't care which point it is where they intersect, we just need a point. So I'm going to see if anything eliminates. Let's try and eliminate the z by multiplying by 2. So I'll have 6x plus 4y minus 2z equals 14, and x minus 4y plus 2z equals 0. And this just so happens to eliminate both my y and my z. So I will have 7x equals 14 or x equals 2. So that means that for any point of intersection, x has to be equal to 2. Now, since we don't have anything to solve for y here, that means y could be anything. So I'm going to choose, for example, y equals 1. And then I'm going to take that back to one of the lines and find the z that makes that work. So we'll plug that into the 3x plus 2y minus z equals 7. So we'll have 3 times 2 plus 2 times 1 minus z equals 7. And figure out what z has to be for this point. So again, we've just found a point on the line of intersection. When we eliminated, it turned out that x has to be 2 on that line. But since y disappeared from the equation and we can't really put it back in there, y and z can be anything with respect to some parameter. They just have to all work together into the equation. So if we can choose one of the variables, y or z, we can solve for the other one. So I'm going to get 6 plus 2 is 8 minus z equals 7, and then that gives me negative z equals negative 1, so I have z equals 1. So my point P is 2, 1, 1. I'm sorry, this should be, nope, that's right, we have 2, 1, 1. Okay, so from there with our ABC, which was 0, negative 7, negative 14, and did it say which version it wanted? Parametric equations, okay. Parametric equations, so we would have x equals a, which is, x1, which is 2 plus 0t, y equals 1 minus 7t, and z equals 1 minus 14t. So that all came down to finding these parametric representation of the line of intersection between those two planes, which is here. Okay, so let's talk about distance with respect to planes and with respect to lines. So the first formula we have here is the distance between a point and a plane. The distance between a plane and a point Q that's not in the plane is found by the projection of PQ onto N, and then you take the magnitude of that, or that's just PQ dot N divided by the magnitude of N. So whichever, details you have, this is the easiest way usually to go about it if you can. P is the point in the plane and N is normal to the plane. So this says find the distance between the point 284 and the plane 2x plus y plus z equals 5. So the N here for this plane is going to be 2, 1, 1 because I'm going to pull it from the A, B, and C of that equation. This is going to be my Q. So I need a point P in the plane. And this is what trips up students sometimes because it could be any point as long as it satisfies this equation right here. So if I choose two values for x and y, I just need to find the z that goes along with it. And since we've only got, it could be anything. So basically what I'm going to do is I'm going to find the z, say z-intercept. I can find the x-intercept. I can find the y-intercept. It doesn't matter as long as it's in that plane. So I'm going to choose x equals 0 and y equals 0. And if I plug those in, that gives me z equals 5. So I found the z-intercept and I get p equals 0, 0, 5. Now the reason I need that p is because for this formula to work, I need pq. So pq will be 0 minus 2. 0 minus, actually I'm going in the wrong direction here. 2 minus 0, 8 minus 0, and 4 minus 5. It would have worked the other way. It would have just changed, it wouldn't have changed anything because of the absolute value. But either way. Okay, So d then, the distance, is going to be the absolute value of the dot product PQ dot n divided by the magnitude of n. So that'll be the absolute value of 2 times 2 plus 8 times 1 plus negative 1 times 1. And then the magnitude here will be the magnitude of n, which is the square root of 2 squared plus 1 squared plus 1 squared. So that gives me the absolute value of 11 over the square root of 6, or 11 over the root of 6, or 11 root 6 over 6. And that is the exact value of the distance between the point Q and the plane that we were given here. All right, this is a different formula. The last formula gave us the distance between a point and a plane in space. This one gives us the distance between a point and a line in space. So you have to be very, very careful with that. In this case, PQ is still a point on the line, or P is a point on the line, Q is a point not on the line. U is the direction vector for the line. So U is just that ABC that comes from the line's equation. So this is a pretty simple formula to use as long as you can do a cross product. It says find the distance between the point 1, 5, negative 2 and the line given by the set of parametric equations x equals 4t minus 2, y equals 3, and z equals negative t plus 1. So coming off of these equations, we can see that A is 4. I know these are written in a different order than you're used to, but the 1 multiplied by t is the ABC, the other one is the x1, y1, z1. So just be real careful about that. So that means in this case that B is 0 since there's no t in this equation, and C is negative 1. So our direction vector U is going to be 4, 0, negative 1. We also need to find P. Now last time we found P by picking values of x and y and solving for z, but that's because we were given a symmetric equation, or we were just given an equation of a plane. In this case, we've got lines, so you'll either be given parametric equations or symmetric equations. And if you're given symmetric equations, it'll be similar to the last problem, finding the P. But if you're given parametric equations, you can just choose a value of the parameter. So we're going to choose t equals 0. Remember, as long as there's no restrictions on t, t can be anything. So I'll have x equals 4 times 0 minus 2, which is negative 2, y equals 3, and z equals negative 0 plus 1, or 1. So my P is going to be negative 2, 3, and 1. So from here, we're going to need PQ. It's the next part of the equation. So PQ is going to be, this is Q, so we'll have 1 minus negative 2, 5 minus 3, and negative 2 minus 1. So that gives me 3, 2, negative 3. So the next part is I need PQ cross U. So I've set up my determinant with I, J, and K, and PQ and U. And when I follow through that determinant, I get negative 2I minus 9J minus 8K. So D then, the distance, is the magnitude of that vector PQ cross U divided by the magnitude of U. So that'll be the square root of negative 2 squared plus negative 9 squared plus negative 8 squared divided by the square root of 4 squared plus 0 squared plus negative 1 squared, which gives me the square root of 149 when I add all that together, divided by the square root of 17. And rationalizing that, it's not super pretty, but we get the square root of 2533, 2533 divided by 17. And that is my distance. So the key thing here is just to make sure you read the directions and you know whether you're finding the distance between a point and a line or a point and a plane, because it does make a difference.